We all know every object in this world has its own architecture. Like human has its own architecture, car has its own architecture, even building and offices has its own architecture. So architecture defines how functions work. So the same way computer, it has its own architecture on which computer runs. So there are two types of architecture. First, the von Neumann architecture. And second, the Harvard architecture. So architecture is also known as a computer model. So let's discuss the von Neumann architecture in detail. So the von Neumann architecture was designed and developed by a great mathematician and scientist, John von Neumann, in the year 1945. So most of the computer today's world will run on a von Neumann architecture, whether mainframe or a personal computer. So let's discuss. Let's see the architecture. So first, input comes and stored in the memory. The input becomes the command and ready to process in the processor. So and fetch the command from the memory. So there is the two process. First, the CU or the control unit. Second, the ALU or arithmetic logic unit. So the role of the CU is to manage and command the input-output, and ALU is to perform the mathematics function after processing completely the control unit. So the control unit stores the result in the memory and displays the output. So this is the working of von Neumann architecture. So let's discuss the components. So first, the input. Input comes through input device like keyboard, mouse, and etc. So second, the memory. The data temporarily stores in the memory called RAM. So number three, process. Process has two parts. First, the control unit. The CU works like a traffic cop. It control and manage the process and input-output. The control unit fetch and store the data to the end from memory. So second, the arithmetic logic unit, or ALU. The role of the ALU is to perform mathematics calculation like addition, subtraction, and multiplication and division. So for the output, the output displayed through the monitor or printer and etc. So let's understand the von Neumann architecture in example. So for example, we enter a 20 plus 20 through the keyboard, and the data is stored in a memory called RAM and ready to process. The control unit fetch the command and check which command to be performed, and if it is arithmetic operation, the CU command to the ALU for the operation. So ALU perform the addition and send back the result to the CU. So the CU store the result in the memory and display it through output device like monitor. So next, Harvard architecture. The Harvard architecture is a computer architecture which physically separates storage and signals pathway for instructions and data. So why do we talk about Harvard architecture? So we basically have got the physically separate memory for instructions and data, so each has its own bus. So obviously the impact of this is that the CPU can access instruction and read and write data at the same time. So basically what that means is if we have a circuit of given complexity of a von Neumann architecture, and we have the same complexity circuit for Harvard architecture, the Harvard CPU is going to be faster because it doesn't experience the same bottleneck. So obviously in a modern CPU, let me just recap our wind over. So Harvard architecture kind links to a RISC processor links to a RISC processor more in the way it is, okay? The way it's set up. Okay. So RISC CPUs use Harvard architecture, not exactly classical Harvard architecture, but a version of it. So obviously, in a modern computer, you don't have physically separate memory. We've just got the RAM, and then you have your storage, which you can load programs from the RAM for execution. So it's changed now slightly, but the classical way of looking at it is the separate memory for instruction, and they are avoiding the bottleneck. So if we're going to compare the two, you can see the left side on the von Neumann architecture, the main memory holding programs and the data. Therefore, they are contending for control of the data bus, which will slow the actual performance down, creating a bottleneck. So on the right hand side, you've got the CPU in Harvard architecture, which two separate physical memory components, and for holding the data and one for holding the program. So back in the that alone, let's not make it over complex now. Alright, basically you should be able to think about what is the advantage of the Harvard architecture competitive on Neumann, and when you think about that, you should be able to bring up that our previous diagram in mind and discuss the fact that you have two separate physical memory location, which negates the bottleneck experience and the von Neumann architecture. Thank you.
Von Neumann architecture disadvantages. Serial instruction processing does not allow parallel execution of a program, since parallel execution are simulated later by operating system. One bus is bottleneck. Only one information can be accessed at the same time, because the single bus can only access one of the two classes of memory at a time. Throughput is lower than the rate of which the CPU can work. Kahit tumaas man ang takbo at memory size nito, nagiging problema pa rin ang bottleneck. Instruction can be stored memory as the data can be accidentally deleted by an error in the program. Advantages. Control units gets data and instruction in the same way from the memory. It simplifies design and development of the control unit. Data from the memory and devices can access in the same way. Memory organization is in the hand of programmers. Harvard architecture advantages. Since it has two memories, which is the program memory and data memory, this allows parallel access to data and instruction. Second, data and instruction are accessed in the same way kasi nga dalawa yung memories niya. So respectively, it has two corresponding buses for accessing these two memory spaces, at saka nagre-reduce yung bottleneck experience ng Harvard architecture. Development of control is expensive and need more time. Ang nagpapamahal nito ay ang pagpapaunlad ng control unit ng Harvard architecture kaysa sa nauna dahil sa komplikado ito. Both memory can be used in the different cell size. So generally, two memories would be present, one for data and on the other one for instruction. They have different cell size, making use of the resources very effectively. Disadvantages. Free data memory can't be used for instruction and vice versa. The unoccupied data memory cannot be used by instruction, and the free instruction memory cannot be used by data. Memory dedicated to each unit has to be balanced carefully. Production of a computer with two buses is more expensive and needs more time. Control unit takes more time to develop and is on the expensive side. It is not used widely, so the development of it would be on the backwards stage. So on the other hand, it does not make most of the central processing unit always. The architecture of von Neumann. First, input comes in. It will gonna store in the memory. The input becomes the command ready to process. The processor fetches the command into the memory. There is two parts in the process, CU and ALU. CU means control unit and ALU means arithmetic logic unit. The role of the CU is to manage the commands in input and output. ALU is to work to perform mathematics function. After processing complete, the control unit stores the result in the memory and display the output. So this is the working of the von Neumann architecture. Kikita natin sa diagram to na dalawa yung memories niya, program memory at ang data memory, na may two corresponding buses for accessing these two memory spaces, kung kaya nare-reduce yung bottleneck experience ng Harvard architecture. Remember, Harvard architecture is primarily used for embedded computers and signal processing, while von Neumann architecture, this is better in desktop computers, laptops, workstations, and high-performance computer. Harvard architecture has two memory and two buses, while von Neumann architecture, one bus for data, instruction, and service is a bottleneck.
Quantum computing is use of quantum phenomena such as superposition and entanglement to perform computation. Computers that perform quantum computation are known as quantum computers. Quantum computers are believed to be able to solve certain computation problems such as integer factorization, which underlies RSA encryption substantially faster than classical computers. The study of quantum computing is a subfield of quantum information science. Quantum computers are different from digital electronics computer based on transistors. Quantum computation uses quantum bits called qubits, much more faster and many times more powerful. Actual quantum computers is still in its infancy, but experiments have been carried out in which quantum computational operations were executed on a very small numbers of quantum bits. How quantum computing works? Quantum computers perform calculation based on the probability of an object's state before it is measured, instead of just 1s or 0s, which means they have the potential to process exponentially more data compared to the classical computers, performing an unimaginable numbers of operations in shortest time possible. Quantum computers inspire the imagination. Their task to crack complicated questions.
Quantum computing is the use of quantum phenomena such as superposition and entanglement to perform computation. David DeTouch, Oxford University Theoretical Physics, is accredited with being the father of quantum computing. And this is also the people who are invented by quantum computing. First is Isaac Chuang from Los Alamos National Laboratory, Neil Gristenfield of the Massachusetts Institute of Technology, or MIT, and Mark Cuban of the University of California at Berkeley. They created the first quantum computers, 2-qubit, that could be loaded with data and output a solution. How quantum computing works? It is performing calculation based on the probability of an object that states before it measured instead of just is, which means they have the potential to process exponentially more data compared to classical computers. Then, quantum computing has also its own programming language, and this is SILQ, is the very first high-level programming language for quantum computing. First programming language that automatically identifies and erases values that are no longer needed. And Netherlands is the leading players in quantum technology as it is developing rapidly worldwide. This is the country has a quantum computers. Then, how much quantum computing costs? The single qubit will set you in $10,000, and that is before. But for now, this is $10 billion. This for a machine whose the true commercial value is far from guaranteed. Then this is also the 10 companies working in quantum computing. First is Accenture, Alibaba Group, Amazon Bracket, AT&T, Atos, Quantum, Baidu, Google, Quantum AI Lab, IBM, Intel, Microsoft. Then quantum computers or quantum computing has also its advantages and disadvantages. The advantages is quantum computers have the potential to revolutionize computation by making certain types of classically interactable problem solvable. While no quantum computers is yet sophisticated enough to carry out calculations that are classical computers can't create, progress is underway. Then the disadvantages is quantum computers are exceedingly difficult to engineer, to build a program. As a result, they are crippled by errors in the form of noise, faults, and loss of quantum coherence. Then this is all quantum computers has also opportunities. First is you can simply work with much more information. Quantum computers can solve problems that are impossible or would take a traditional computer in practical amount of 1 billion years to solve, or virtually unbreakable encryption. Quantum computers will change the landscape of data security. Then, a physics major with theoretical computer science focus can help on designing algorithms for quantum computers. Then, quantum computing be used in business, technology firm, and this is also super fast algorithms for data search and artificial intelligence or discovery of new pharmaceutical molecules expected to be millions of times faster than the device you're using right now. And there is also a risk in quantum computing. First is the collapse of asymmetric cryptography, your bank account, military communication, to health records, and exposing private data. But there is also a good news. The good news is this apocalyptic break the internet scenario is preventable if we act right now. And activities that will be vulnerable in the quantum computing era is first, online banking, cloud computing, online gaming, e-commerce, email, device updates. And this is also the information from today that could be decrypted by quantum computers in the future. Emails, credit card numbers, medical history or genetic information, juvenile criminal records, executive communication, drug trial data, intellectual property, information transmitted between cloud data centers, state-to-department cables communication between Department of Energy laboratories, information on facilities, physical security protocols. And this is also prevention is possible because they are also invented a PQC or post-quantum cryptography. These experts are currently developing PQC solution, but this will be needed to standardize and widely adopted that could take years or even decades. The US government recently took steps to accelerate quantum research and developing, including the passage of the National Quantum Initiative Act and cryptography that would be defend against quantum hacks. Thank you.